Today I'm going to be presenting the solution to the practice problem for the second homework. All right, to restate the problem, we have a plane wall which is at steady state. That wall has a thermal conductivity, which we write as K, of 50 watts per meter Kelvin. And it has a thickness of 50 millimeters, which I always work in meters, so we're just going to write 0.05 meters. Now, they tell us the temperature distribution inside of that wall, which we write like this, A plus B x squared, where A is 200 degrees Celsius and B is negative 2,000 degrees Celsius per meter squared. And those units will make more sense as we work the problem. Okay, and we are asked to find what is the rate of heat generation inside the wall, or what is Q dot. Now this is what we call an inverse problem. Normally we're given something like Q dot and K and asked to find the temperature distribution, but now the problem's been reversed. Okay, so what we're going to do, next step, is our energy balance. Let's draw our plane wall, which is just going to look like this. And we have our control volume, which is infinitesimally wide. So it's just a very small width. And into it, we have heat conduction, which we'll write as Qx. Coming out of it, we have additional heat conduction, or what's leaving our control volume, Qx plus dx. And then inside that control volume, we have some energy being generated, thermal energy being generated that probably was electrical energy before. And we'll write that as Q dot. So here's our energy balance, and you'll recognize this as the beginnings of how we derived the heat diffusion equation. So let's list our approach for this problem. We're going to simplify the heat diffusion equation, which I'll always abbreviate as HDE, and then we're going to solve for Q dot. Likewise, they also ask us in this problem to find the heat flux at the boundaries of the wall. Okay, so that's going to be our approach today. In order to do that, we're going to write out the heat diffusion equation. This gets a little long, stick with me. So remember, our first term is the second partial of temperature with respect to x. And this accounts for the change in heat conduction in the x direction. We also have those terms in the y direction and in the z direction. Then we add any energy that is generated inside of our control volume. And finally, our last term accounts for any of that energy that remains in our control volume, doesn't leave as conduction, but stays as thermal energy, manifesting as an increase in temperature. So here's our famous heat diffusion equation, in this case for constant properties. Now we know it's a plane wall, which means this wall is infinite in this direction and likewise in and out of the screen. So what that means is we can get rid of the y term and the z term. Since it's infinite in those directions, there is no conduction. The temperature is the same at all points in those directions. Likewise, we were told it's steady state, which means no energy will be stored inside of our control volume. So we can get rid of that term. So we are left with this case, d squared t dx squared plus q dot over k equals 0. Now, we already know t, right? We're looking for q dot. We know k. So all we have to do is perform these mathematical operators on our temperature distribution t, which is given to us here, and then plug it into this equation and we can solve for q dot. So let's do that. With T of x equal to a plus bx squared, we're going to first, this can be rewritten like this, or the derivative with respect to x of the derivative of t with respect to x. So with this equation, we're going to first take one derivative, dt dx, which is 2bx. Now we take the second derivative. So now we're taking the derivative of this expression, and that just gives us 2b. Okay, so now all we need to do is plug what we just found back into our heat diffusion equation and solve for q dot. So we have 2b plus q dot over k is equal to 0, which means q dot is equal to minus 2bk. We subtracted this to the other side and then multiplied by k. So when we plug in our value for b and our value for k, and we already know what 2 is, then we can get minus 2 times b, which is minus 2,000 degrees C per meter squared, times our thermal conductivity, which is 50 watts per meters Kelvin. Now there's been some confusion. How is it that we're able to cancel our temperature in Celsius with this, which is in Kelvin? But both of these represent a temperature difference. In this case, thermal conductivity, we had to take a temperature difference in order to find what that value was. Likewise here. Since it's a difference, then we can cancel Celsius and Kelvin. So doing that calculation, we are left with 200,000 watts per meters cubed. And that is the value we are looking for Q dot. So now it remains to find the heat flux at each wall. Okay, in the second part of the problem, we're asked to find the heat flux that exists at the boundaries of our wall. In other words, right here and right here. You'll remember that we have the temperature distribution in our wall already in that form. So what we're going to do is we know the temperature distribution in this wall, which means we're able to use Fourier's law of heat conduction, or the heat flux at any point within this wall is equal to the negative of the thermal conductivity times the derivative of our temperature distribution with respect to x. In this case, evaluated at a certain point where we want to know the heat flux, where x has its origin here on the left side. Okay, so now we just need to apply this to both sides, and we've got our heat flux. So first, we'll do it at x equals 0, or this leftmost part of the wall. So Q double prime, this is a heat flux at x equals 0, is minus k times the derivative of the temperature distribution, which you'll remember, we'll do this down here, is equal to 2bx. Well, this one's pretty simple because x is equal to 0, and with that 0 in there, the whole thing becomes 0. So the heat flux on our leftmost part of the wall is 0, which means that this is actually an insulated wall right there. Now, it won't be quite so simple when we go to T, at x equals T, or the rightmost surface of the wall. Now, since we have heat generation inside of our wall, and this is insulated, all of the heat that is generated in here is going to move this direction and leave out that surface. Okay, so our heat flux at x equals T, again, using Fourier's law of heat conduction, is It's going to be that expression, but now instead of x, we're going to plug in t. Okay, using our values of k and for b and for t, we can plug all those in, and when we evaluate that expression, remembering that b is a negative number, we get 10,000 watts per meters squared. Okay, so we had 0 at the left wall, 10,000 at the right wall. So the last part of our problem is our discussion. In this case, I would probably point out that the left surface is insulated because that was an interesting find. And sometimes it's good just to state again what it was we were asked to find. Okay, that is our problem. Thanks for watching.